Oh man, what's up with all these functions? How am I gonna use this in real life? This makes zero sense, bruh.
I'm gonna make it fall.
Hey everyone, welcome back to our channel. Today, we're stepping out of the classroom and diving into real-world math. From money, or even on the road. Stick with me and see how math is everywhere. We've all ridden a bike before, right? But did you know that just by pedaling, you're making waves? Let me show you what I mean. Alright, now let's talk about the wheel. So basically, the single point on the edge goes up and then goes back down and then goes back up again, which is called a sinusoidal function, and could method it by using a sine function.
If we were to take a closer look at the bike and graph it as a circle, here's what it looks like.
We can graph this motion using a function like this. Here's what the variable means. A is the amplitude, the radius of the wheel. B controls the frequency, how fast the wheel is spinning. C is the horizontal shift, when the motion starts. And D is the vertical shift, the height of the wheel's center.
As the wheel turns, that point rises and falls, just like a wave. So if you track its height over time, you'd get this beautiful curve right here. Okay, so here's how we graph it. There's two types of graph, a cosine graph and a sine graph. So for the cosine graph, should look something like this. It starts from the top and then go down and then back up. Meanwhile, a sine function will start from the midline. So something like this. Start from the midline, goes up, down, and then goes back up. So it's basically like a horizontal shift. See, if we were to put them together, it should look something like this. It's like a horizontal shift of the cosine. So next, let's explain the variables. So first is the amplitude, the A. Let's make it blue. So the A is the distance from the midline to the highest point, or the midline to the lowest point. So this part right here is the A, the amplitude. Same thing goes for the cosine. This point right here is the A, and this point is also the A. It's the same distance. That's how the A affects the graph. So as stated in our example earlier, which was the bike, the radius of the bike is the A. So if the radius of the bike is smaller, that makes A smaller as well. If the radius of the bike is bigger, then the A will become bigger. Next up is the B. The B is the frequency. It's how frequent the waves move in a period. So a period, first of all, let's understand what a period is. A period, let's name it purple. So a period is from this point right here, the starting point, all the way to the end. One way that we can recognize it is, so this entire thing is a period. One way we can recognize it is from any top point to the next top point. So like this is the highest point of a cosine, and the next highest point is here. So that distance is the period, although this graph is not drawn to scale, but it should give you a good idea of it. And for the sine graph, we can take a look at from the midline to the second midline, not this one, but the second one, or from the highest to the next highest, which we can see in cosine easily. But for sine, we can look at it from here to here. So the second midline that it meets, not this one, because then it'll cut off the second part of the graph. That's the V, which is the frequency. If the B is higher, then it will be more frequent in between that period. So in this period, it moves one time. But then if the B is higher, then it should be more frequent. It should look something, let's change color. Should look something like this. You a better idea of it. So like this. So this is the green graph is when it has been when B has been doubled twice. So as we can see from the first graph, the yellow one, it moves, there's one period, and then it moves one time, the b is 1, but then in the second one, b is 2 times. Why? Because it repeats itself twice. From here, this point to this point, that's 1, and then from this point to this point, that's another one, so it's 2. So the b is how frequent it is. So as from the example in the bike again, if the bike moves slower, then the b is smaller, but if the bike moves faster, then b is bigger as well. Okay, let's pause it right here and see Anthony shows us.
Okay, now let's see how the speed of the bike affects the function. So basically first, I'll start off slow and then I'll go faster and faster.
So as we can see here, when he's pedaling the bike slower, it changes the graph by affecting the b, which is the frequency, making it smaller. However, in this second clip, we can see that he's pedaling the bike faster. This will increase the frequency of the waves in each period, increasing the b. Next up is the c, which is the horizontal shift within the graph. It basically just depends on the location of the point where we start off on our bike. That's the horizontal shift. And then for the vertical shift, it's the height of the bike. So like in this case, horizontal shift would be 0, because this is already 0, and then that's how it starts. But then for our graph in the bike, it should start off like in here. If it's a cosine, it should start like this, because it cannot be negative, because we're not going under the ground, we're on top of the ground. So the distance of the bike would be the distance of the bike from the bottom to the top point of the wheel. That would be our vertical shift. Okay, let's get back to Anthony.
So basically, sinusoidal motion shows up everywhere, not just in wheels. It'll show up in sound waves, heartbeat monitors, or even ocean tides. Every smooth and repeating patterns, that's just cosine or sine doing its thing. So next time when you're riding a bike, just remember, you're not just riding a bike, you're tracing a whole wave of math behind you. Catch!
From spinning wheels to speeding scooters, let's see what happens when speed meets distance.
Okay guys, let's pause him right here. Before we move on, we have to understand that our formula is v equal d over t, where v is the velocity, d is distance, and t is time. Okay, he can continue now.
We'll be doing 3 runs at 3 different speeds at 15, 25, and 35 kilometers per hour.
And I'll be the timekeeper.
I will be doing the first run at the slowest speed at 15 kilometers per hour.
And I'll be waiting at the finish line.
Okay.
Ready, set, go.
Guys, why is he going so slow? What was that? This is actually really slow, kind of awkward. Okay, he's here now.
16.74.
Okay guys, round 1 done. Now let's go
Time
for
the
round 2.
second speed at 25 kilometers per hour.
Ready, go.
Okay, this is round 2 at 25 kilometers per hour. Should be faster than the one from round 1. Okay, so yeah, it's a little bit faster. Okay, now without looking at the time, guess how long it took. 3, 2, 1. 12.61. Okay, now it's time for round 3.
Now I'll be doing the third run at 35 kilometers per hour.
Okay, 3, 2,
Go.
1. Oh wow, this one's a lot faster. Oh, he's already here.
9.8.
Okay, let's pause him and look at our data. Okay, now that we've already did our experiment, let's take a look at our data. So first up is we need the rounds, the speed, distance, and the time. So for round 1, the speed was 15 kilometers per hour and distance was 70 meters. The time it took us was 16.74 seconds. For round 2, it was 25 kilometers per hour with the same distance of 70 meters and time was 12.61 seconds. Round 3 was 35 kilometers per hour, still the same distance, and 9.8 seconds. So with that, let's take a look at our calculations. Okay, so first we'll start off with the round 1, and let's say we're trying to find v. the velocity or the speed. So we know that v is equal to d divided by t, distance over time. So since d here is 70 meters, we'll just put it here and then change it to kilometers, which is 0.07 kilometers, and t, which is 16.74 seconds, and change that to hour. So after our calculation, we got v is equal to distance over time, and then our answer is 15.05 kilometers per hour. So comparing that time to our speed right here, it's fairly similar. That means our calculation and our experiment for round 1 was true. It was pretty accurate, seeing that it's only 0.05 kilometers per hour apart. That was a successful experiment. Now time for round 2. So let's take a look at our calculation. So same formula, v is equal to d over t, distance over time, and d is still 70 meters, 0.07 kilometers, and t is 12.61 seconds, which is 0.0035 hours. So with that, let's calculate it. 0.07 divided by this is equal to 20 kilometers per hour. So from that, we can see that it's a little bit lower than our speed, which was 25 kilometers per hour. So therefore, we can conclude that for this experiment, it is not as accurate as the experiment number 1. So it's either there was something wrong with our distance, the timing, or other outside factors. But overall, this wasn't as bad, and let's take a look at round 3. Okay, round 3. So our speed for this round was 35 kilometers per hour, same distance, and 9.8 seconds. So same formula, v is equal to d over t, and d is 70 meters, so 0.07 kilometers, t is 9.8 seconds, which is 0.0027 hours. Now with that, let's do our calculation, and we've got 25.92 kilometers per hour. So that's way off our speed, so there must be something wrong with our distance during the experiment or something else. But overall, this experiment was not accurate at all compared to round 1 and round 2. This was the experiment that was the furthest off, because there's always mistakes during an experiment, and it's the fact that we learn from them. Let's take a look at this comparison. Why didn't our experiment match the math perfectly? Well, that's because real life isn't as clean as a textbook equation. First off is human error. Our timekeeper might have started or stopped the watch a little bit too early or too late. So even if it was just 1 second delay, it can still throw off the whole result. Secondly is the distance. Even though we said 70 meters, but measuring that exactly outdoors can be a little tricky. With a few extra missing steps, or missing steps, it can make a huge difference. Not only this, but our distance can vary from experiment to experiment, but we can see that experiment 1 must have had the most accurate distance. Thirdly is the scooter's speed. It wasn't perfectly steady either, so even just a slight slowdown or a wobble can change how long it takes to finish. So with all these little factors, the reaction time, the distance accuracy, the uneven pavement, or all of those things, they all add up. But that doesn't mean that the math is wrong. The equation still shows us the relationship, which is that speed will increase as time decreases. That's the inverse variation, a classic rational function. So yeah, real life experiments aren't perfect, but the function still helps us to understand what should happen, and that's the beauty of applying math in motion. But anyway, let's put this into a graph and let's look at the rational function. Okay, so we'll just open up decimals and then put in our datas. So the x-axis will be the independent variables or the input values, which is the speed, and then the y-axis will be the dependent variables, also known as the time, where it depends on our speed during our experiment. So our first one was 15 kilometers per hour at 16.71 seconds. And then the second one was at 25 kilometers per hour at 12.61 seconds. And then the third one is 35 kilometers per hour at 9.8 seconds. So let's take a look at it in the graph. So it works like this. Let's break down what's happening with the math here. We tested 3 different speeds, 15, 25, and 35 meters per second, and then timed how long it took to travel the same 70 meters distance. When we plotted those points on a graph, we've noticed something interesting. The faster the speed, the shorter the time, but the time didn't decrease in a straight line. Instead, the curve bent downward. That's because this relationship isn't linear, it's inverse. Mathematically, we modeled it using a rational function, where t is equal to seconds and s is the speed in kilometers per hour, or we can do it in is measured in hours, and then speed is still in kilometers per hour. It depends on just us changing the measurements. So this equation tells us the time is inversely proportional to speed. Double the speed, you cut the time in half. So while our graph isn't a straight line, it still shows a very clear trend. So as x approaches infinity, f of x approaches 0, but it does not reach 0. That's the heart of a rational function, 2 quantities changing in opposite ways, but still connected through division. Rational functions aren't just on paper, they show up every time you move with speed, from cars to runners to scooters. Distance and speed are always locked in a math equation. So next time you're racing down the road, just remember, every second you save is a function in motion. From racing time to taking your time, not every function is about speed. Some is about building, little by little.
Guys, I want the shoes. But now, I currently have $0.
Anthony currently has $0, but don't panic yet. This is where arithmetic sequences come in. The arithmetic sequence formula is a of n is equal to a of 1 plus d multiplied by n minus 1. In this case, a of n will be the amount of savings after n weeks. A of 1 will be the first week's of saving, and d is the amount of money added to each week.
Let's say I save $5 every week. So week 1, I have $5, week 2, $10, and week 3, $15, and so on. So guys, this is my first week, and I'm gonna put $5 in the piggy bank.
Let's watch Anthony start his 20-week journey to saving for his new running shoes. Week 1, $5. Week 2, $10. And week 3, let's see how much. You guessed it, it's another $5. So $15 already. And he will continue to do this for 20 weeks and so on. So, this is a perfect example of an arithmetic sequence, a pattern where the same number is added again and again. So if we plot this on the graph, the points line up in a straight line. That's because it's a linear growth pattern. The amount of money grows steadily over time. And every week it's the same move, $5 in. No magic, no tricks, just pure arithmetic. That's the beauty of a linear function. Same input, same charge, predictable outcome. So by week 6, it should be $30, so in week 7, $35 already. Each step might feel small, but stack enough of them and you've got momentum. Remind you of anything? Like growing your follower count 1 post at a time or leveling up in a game? That's the same thing. So if you save $5 every week for a whole year, that's already $260. Enough for a new pair of shoes, concert tickets, or maybe even investing in your next big idea. And hey, at least Anthony's piggy bank is finally getting the attention it deserves. Week 12, already another $5. This isn't just a stack of bills, it's a story of growth, one that follows the equation a of n is equal to 5 of n. Or we can use the other equation that was shown earlier, which was a of n is equal to a of 1 plus d multiplied by n minus 1. So far, we're already on week 14. That's already $70 in the bank. And no, he didn't win the lottery, he just saved up money, little by little. So let's be real, saving money isn't flashy. It's not viral, but this is how real goals are built. Saving little by little, one by one, at a time, without giving up. $5 a week might not sound like much until you zoom out. So just saving little by little, and he's already on week 19. Almost there already, just one more week left and he's got his new shoes.
Okay guys, 20 weeks passed by and now I have enough to buy a shoe.
Okay guys, so Anthony just bought his new shoes, but let's just pause him right there and let's take a look at the graph and analyze it real quick before we let him celebrate his new shoes. Look at the graph. So we can write the equation like this, where y or a of n is the same. A of 1 is $5 because he started off at $5, and the d is also 5 because he added $5 for each savings, and then n can be replaced by x. So this is what the graph should look like after plotting it. So to make sure, let's just add a few numbers from our experiment to see if it matches. So at week 1, we've already established that it's at $5. So the point is on the graph, so it's accurate, but let's not say anything yet, and let's see, let's continue first. So week 20, it's $100. That's also correct, it's on the graph. And halfway, let's say week 10, where he earns $50. That's also on the graph, it's right here. And let's try a few more. Week 2 should be $10. Oops, $10. Yeah, that's also on the graph. What else? Let's try week 12, should be $60. Also correct. Therefore, we can see that this graph perfectly aligns with Anthony's saving. So from this, we can see that it's a linear graph. So arithmetic sequences follows a linear graph. Okay, now we can continue. Oh my god guys, look how happy he is, just jumping around with his new shoes. That's what money can do, and that's what arithmetic sequences can also do.
Okay guys, math helped me went from broke to have enough money to buy new shoes.
Okay, wait, we don't want to pause him too much, but what happens if he saves up more than $5? Or what happens if he saves lesser than $5? How will this affect the time that it will take him to reach his goal? So let's take a look. What happens if he saves more than $5? Let's say he saves up $10. So $10 per week. And we know that the formula is a of n is equal to a of 1 plus d multiplied by n minus 1. And in this case, our d is $10 per week. It is the common difference, as already mentioned earlier. And a of 1 will be $10 because by week 1 he will saved up $10. And a of n will be $100 because the shoes that he wants is $100. So from this information, we can fill in the values and we can look for look for n. So $100 for a of n, $10 for a of 1, 10 for d, the common difference, and with that, let's calculate it. So first up, we bring this 10 over to the other side, so we minus it, and then you get 90. After that, divide both sides by 10 to get rid of the d, which will lead to 9 equal to n minus 1. Therefore, we can say that n is equal to 9 plus 1 and n is equal to 10. So from what we've seen here, compared to the experiment earlier, when saving $5 per week, it'll take him 20 weeks. However, if he saves up $10 per week, it'll only take him 10 weeks. That's the difference between saving up $5 and $10 per week. Now, what if he saves lesser than $5? Let's say he saves up $3. So if he saves up $3 per week, then the formula will stay the same, but the D will now change. So earlier it was 10, now the D is $3. A of 1 will also change because the amount he has by week 1 will only be $3 because he only saved up $3. While A of N will still be the same, which is $100 because the price of the shoes still does not change. We're still looking at the same experiment. So with that, we can pull up our formula. So replace in the number and put them in the main formula. So we'll now get an equation of 100 is equal to 3 plus 3 multiplied by n minus 1. So let's do the calculation. First up, again, same thing, minus the 3, move the 3 over here, move it to the other side, you get minus, so you will get 97. After that, divide both sides by 3 and we'll get 32.3. 32.33 is equal to n minus 1. So if we're looking for n, it's 32.33 plus 1. Therefore, n is 33.33 weeks, which is obviously greater than 20 weeks. 20 weeks that he would have gotten his shoes if he saved up $5 per week. So we can see that if he saves up more than $5, then it'll take him lesser time. So it'll take him less than 20 weeks to reach his preferred amount of money, which in our case is $100. But if he saves less than $5, then it'll take more time, more than 20 weeks, to be able to buy his new running shoes. So what did we learn today? Whether you're riding a bike or solving an equation, sine waves are everywhere, smooth, repeating, and predictable. And with rational functions, speed and distance are more than just numbers. They tell a story. The faster you go, the less time it takes. And even $5 a week adds up. Arithmetic functions shows us how consistency pays off. So 3 functions, 3 real-life moments, and 1 big realization that math isn't just in textbooks, it's everywhere around us. Math makes sense. Hey guys, the video editor over here. We really hope you guys enjoyed this video, and thank you so much for watching until the end. We hope you guys learned a lot today, and we'll see you guys next time. Bye! Enjoy the bloopers.
I can't wait for you to come my way. I've been far away, but I'll keep running just to find a way.